Okay, so welcome to Enter the Quacoon, where nature, technology, and spirituality converge. This week's storm in Texas was a wake-up call to the dangers of climate change. Failure to achieve zero net emissions by 2050 will have disastrous consequences. This week, we focus on how adiabatic quantum computing can be used in our attempts to tackle at least a few aspects of this enormous problem. We have with us today Sudeshna, who's currently working as a software engineer in the quantum industry. She has a master's degree in physics from the University of Glasgow. Her final thesis attempted a calculation of the charm content of a proton to ultimately aid in the direct detection of dark matter. She also completed a project on the use of artificial neural networks and boosted decision trees in the search for Higgs boson. She's also worked as a radio content creator, producer, and presenter. Hi, Sudeshna. So we'll get started with your experience working in quantum, or your thoughts on working with quantum so far.
Okay, so I guess my introduction to quantum was very much within my degree. We had to do 3 to 4 years of quantum theory before we really started to understand the applications of quantum mechanics in subjects like quantum information. And that's really what started the real interest towards all the different ways that quantum could have a real advantage towards the future in so many different industries. When you wake up to the idea that most of the problems that we can't solve these days is optimization, constraint satisfaction problems. And that's exactly where adiabatic quantum computing has really made such an impact, especially companies like D-Wave that are creating hybrid machines such as quantum annealers that are able to sustain architectures of thousands of qubits because of the processes that allow the qubits to not have so much interaction with the environment, which gate theory quantum computing doesn't do. Gate theory quantum computing very much has a lot of interference with the qubit system in trying to manipulate it from beginning to end, which could, because of the level of R&D in materials discovery at the minute, does mean that the qubits can experience decoherence, which is information loss from skipping up to a high energy level by retaining too much heat in the environment and adding a lot of noise to very sensitive calculations that require many systems of qubits. And because all of these systems of qubits are what we call entangled, the minute that one qubit collapses into a state, they all collapse into a state. So it's a very fragile system.
Right.
Waves, quantum annealers are particularly good for handling these kind of constraint satisfaction problems that require so many systems of qubits, because it sets up the constraint objective at the very beginning of the annealing process, doesn't touch the system at all, and allows it to settle into the lowest energy state, which is what every system wants to do anyway. And the reason for all of the thousands of qubits is because if you think about the way the qubits work, the position of ones and zeros allow a one qubit to be able to compute 2 calculations, just one qubit, and then 2 qubits to be able to do 4. 3 qubits will be able to do 8. By the time you get to 10 qubits, which is a fairly small system, you can do 1,024 calculations. That's because, and the way that we work, it scales up to n qubits, to 2 to the n calculations, because each qubit can do 2. And this is kind of this number of calculations is fairly ubiquitous for every problem that a classical computer would find really difficult to solve, because it would just require having to
Hamiltonian and then go through that evolution process and reach the final Hamiltonian, which basically encodes a solution to the problem you're trying to solve.
Yeah.
So, and that is, I guess, a very effective method to solve a limited set of problems, especially optimization. And so that brings us to the next question about what are your thoughts on how optimization, or rather quantum annealing, in the application of optimization will be useful to solve some of the major problems you're facing today, such as climate change or global hunger. So what are your thoughts about that?
It's an interesting question because climate change and global hunger are actually very intimately linked with each other.
Exactly. Mm-hmm.
And solving one is very much a goal towards solving the other. And by one, I mean specifically climate change. Climate change, one of the biggest victims to global hunger is actually small local farmers in developing countries.
Mm-hmm.
And a large part of the reason why they have to go hungry in a period actually known as the hungry season before they make their harvest is because they lose a lot of their harvest to spoilage, which would happen less if they had access to things like fertilizer. One of the biggest optimization problems that would help us towards tackling our goal towards lowering emissions is actually finding a better method for finding catalysts that do the job for towards carbon capture, towards making ammonia in fertilizers, towards hydrogen power. All of these chemical reactions, in order to take place, require a catalyst. A catalyst is essentially something that allows a chemical reaction to take place without exponential energy being used to allow the chemical reaction to take place. It lowers the activation energy. And the reason, at the first time that this discovery was made was during the Haber process. To be honest, I don't know if catalysis itself was found during the Haber process, but the Haber process was groundbreaking for making ammonia, for oxygenating nitrogen to be able to make fertilizer. But there are thousands of catalysts that would actually do a much better job. And in order to be able to find out which catalyst does the most efficient job, you would need to simulate the chemical process, which requires exponential computational resources for our classical computer. But that would be very quickly done on an architecture like a quantum annealer that can handle so many calculations at the same time. And it's not just catalysis towards fertilizers. It would help aid the process of splitting water molecules towards hydrogen power. We currently use a very expensive method using, I think, a platinum catalyst. And both of these, so the use of fertilizer at the minute, the Haber process actually is the cause of 3 to 5% of emissions currently. And this kind of computation is actually very possible within the next decade in the sort of noisy intermediate scale quantum era that we're currently existing in, where the devices are very moderate in size and still quite prone to noise in terms of decoherence. So this is all very achievable within the next couple of years, and it would have a massive impact on reducing emissions. By the time that quantum achieves its aim towards building much bigger systems that are really fault tolerant and can be corrected by error, that all of the sources of being able to tackle climate change, all the other optimization problems that require bigger architecture would absolutely explode. It's going to make it's going to be really revolutionary towards the computational chemistry research.
I agree. Yes. So it's said that chemistry is a killer app for quantum computing right now, because that's where you get the maximum impact with the NISQ era quantum computers, the noisy intermediate scale quantum computers. And like you said, that the ammonia splitting problem is a very high value problem right now, because in nature, I guess it's done using nitrogenase. And it happens at room temperature with atmospheric pressure. Whereas when you do it in the industry, in a factory, you require high pressure. There's a lot of energy wastage. And
but we don't know how to create
we don't know that. Yes. So that process is what needs to be modeled, and it cannot be done using a classical computer. But hopefully it can be done with a quantum computer and then about. So thank you, Sudeshna, for sharing with us your thoughts and opinions on how quantum computing can be used. And hopefully in the near future, we'll hear more from her about her work and her achievements in this field. Thank you again.
Thanks a lot. Thanks for having me.